A chip running on 7 nanometer silicon and a chip running on 14 nanometer silicon doing the same job at the same speed, drawing roughly the same power. That sentence should not be true. For 20 years, it wasn't. It is now. The semiconductor industry has operated on one assumption since Gordon Moore wrote it down in 1965: shrink the transistor, improve the chip. Everything else was secondary. Packaging, the discipline of connecting finished chips to each other and to the outside world, was considered logistics. Necessary, unglamorous, not where the real competition lived. Foundries raced to 7 nanometers, then 5, then 3. TSMC spent decades and hundreds of billions of dollars getting there. The node was the weapon. China couldn't reach the leading nodes. The equipment to build them, ASML's EUV lithography machines, priced at $380 million each, has been under export restriction since 2019. The logic from Washington was clean. No EUV access means no advanced chips, means no advanced AI, means no advanced military systems. A clean causal chain. Here is what that logic missed. The node is one variable in a multivariable equation, and China, locked out of one variable, has spent the last 5 years aggressively rewriting the others. Advanced packaging, specifically chiplet integration, 2.5D and 3D stacking, and heterogeneous die assembly, can recover a significant fraction of the performance gap between process nodes without ever touching a lithography machine. MIT's Research Laboratory of Electronics published analysis in 2023 suggesting that packaging innovations could offset 2 to 3 generations of node shrink in specific workload categories. 2 to 3 generations. That is the gap between TSMC's N3 process and what SMIC can currently produce at scale. China's packaging infrastructure has been quietly scaling for years. Tongfu Microelectronics, JCET Group, and Tianshui Huatian Technology, 3 companies most Western analysts don't mention in the same sentence as TSMC or Intel, collectively handle a substantial share of global back-end semiconductor assembly. They were treated as commodity processors, low margin, low complexity, low strategic importance. That categorization is now a liability for anyone who held it. JCET acquired Singapore's Stats ChipPak in 2015 for $780 million. At the time, analysts described it as a Chinese company buying capacity. What it actually bought was a decade of advanced packaging process knowledge, customer relationships with Qualcomm and Texas Instruments, and engineering talent that understood how leading-edge integration actually worked at the assembly level. Tongfu, through its joint venture with AMD's former packaging operations in Malaysia, absorbed similar institutional knowledge through a different channel. The investment that followed wasn't random. China's National Integrated Circuit Industry Investment Fund, the so-called Big Fund, directed capital specifically toward back-end capabilities after 2019. Not because packaging was the fallback, because someone in that funding structure understood that packaging was becoming the frontier. That distinction matters. There's a version of this story where China's packaging push is a workaround, a second-best option chosen because the first option was blocked. That version is partially true and mostly misleading. The semiconductor industry globally is moving toward chiplet architectures because monolithic dies have hit physical and economic scaling limits that exist independent of any export control regime. Intel's disaggregated Meteor Lake, AMD's 3D cache, Apple's UltraFusion. The leading Western companies are all building toward a world where packaging integration is as strategically important as process node. China didn't invent this direction. It just removed the hesitation to move there. What CXMT is doing in memory stacking, what Huawei's HiSilicon division has been quietly specifying for its next generation of Kirin processors, what the Yangtze Memory Technologies roadmap implies about 3D and architecture extending into logic integration. These are not desperate improvisations. They are coordinated moves along a technology curve that the entire industry is following. The sanctions were designed around a map of the semiconductor industry that was accurate in 2019. The industry has moved. The map hasn't been updated. We'll come back to what that gap between map and territory actually costs, because the number, when you trace it carefully, is not small. The performance gap between a leading-edge node and an advanced packaging solution isn't fixed. It shifts depending on what you're building and what you're asking the chip to do. For general-purpose computing, the kind that runs operating systems, handles file transfers, executes broad instruction sets, node shrink still matters significantly. Transistor density determines how much logic you can pack into a given area, and that advantage doesn't disappear because you've learned to stack dies efficiently. Nobody is arguing otherwise. But for AI inference, for memory bandwidth-constrained workloads, for the specific computational profiles that data centers actually run at scale in 2025, the equation looks different. These workloads are often bottlenecked not by raw transistor count, but by how fast data can move between compute and memory, and how efficiently multiple processing units can coordinate without latency penalties eating the throughput. That is precisely the problem advanced packaging solves, not as a workaround, as a direct architectural response to where the bottleneck actually sits. Huawei's Ascend 910B processor is the clearest case study available in open sources. Manufactured on SMIC's N+2 process, roughly equivalent to 7 nanometer by some metrics, though the comparison is contested, it uses a multi-die packaging architecture to compensate for what the node cannot deliver alone. Benchmark data from Chinese research institutions, cross-referenced against independent testing published in late 2023 by SemiAnalysis, suggested the 910B achieved training performance within measurable range of NVIDIA's A100 on specific transformer model architectures. Not identical, not superior, within range. The A100 is built on TSMC's 7 nanometer process. The 910B is not. That gap, which should have been decisive, was narrowed by packaging architecture. That is the data point that should reframe this entire conversation, and mostly hasn't. There's a counter-argument worth taking seriously before moving past it. The 910B comparison is workload specific. On other tasks, particularly those requiring dense floating-point operations across large unstructured datasets, the node gap reasserts itself and the packaging advantage shrinks. Critics of the packaging closes the gap thesis point to this correctly. A chip optimized for transformer inference is not a general-purpose compute engine, and the inference workloads where Chinese packaging solutions perform competitively are not the same as the training workloads where NVIDIA's H100, built on TSMC's 4 nanometer process, operates in a different category entirely. That objection is accurate. It is also somewhat beside the point. China's domestic AI deployment is not primarily a training problem. The frontier model training happens on clusters, large, centralized, expensive, and increasingly difficult for Chinese companies to build under current export controls. But inference, the act of running a trained model to generate outputs, happens everywhere. In data centers serving consumer applications, in edge devices, in military systems processing sensor data, in telecommunications infrastructure making real-time routing decisions. The volume of inference compute China needs domestically dwarfs the training compute, and that is the market where competitive packaging performance is sufficient. This is the part of the strategic picture that gets compressed in most Western analysis into a single sentence about China being years behind. Years behind on training clusters, possibly. Years behind on the specific workloads that matter most for domestic deployment, no longer clearly true. TSMC recognized something about packaging before most people were paying attention. In 2016, the company introduced its CoWoS, chip-on-wafer-on-substrate technology, a 2.5D integration platform that places multiple dies side by side on a silicon interposer, dramatically increasing the bandwidth between them. NVIDIA's H100 relies on CoWoS to connect its GPU die to its HBM3 memory stacks. Without that interposer, the H100's memory bandwidth, 3.35 terabytes per second, would be physically impossible to achieve. The node gets the attention. The packaging makes the node useful. China's packaging companies have been developing interposer capabilities in parallel. Tongfu's advanced interposer work, JCET's flip chip and wafer-level packaging expansion, and a set of less publicized investments in silicon interposer substrate manufacturing concentrated in Jiangsu and Guangdong provinces. These form an infrastructure layer that didn't exist at meaningful scale in 2018 and does exist now. The yield rates are lower than TSMC's CoWoS line. The process control is less mature. These are real gaps. But yield rates improve with volume, and volume is exactly what China's domestic semiconductor demand, insulated from Western competition by policy and necessity simultaneously, is generating. Remember the three companies mentioned earlier: Tongfu, JCET, Huatian. Here's where that matters. Combined capital expenditure across those three firms from 2020 to 2024 exceeded $4.2 billion, directed specifically toward advanced packaging capacity expansion. That figure comes from their combined Hong Kong and Shanghai exchange filings, not from estimates. $4.2 billion into the one part of the semiconductor stack that export controls don't directly touch. The controls were built around the front end. The investment went into the back end. There is a version of this story that ends with a clean conclusion. China cracked the packaging problem. The sanctions failed. The node war is over. That version is tidier than the evidence supports. Advanced packaging has a ceiling, not a theoretical one, a practical one that shows up in the physics of heat dissipation, signal integrity, and interconnect density as you stack more dies in closer proximity. The more aggressively you integrate heterogeneous chiplets, the harder it becomes to manage thermal output from a package that can't grow arbitrarily large. TSMC's own engineers have described 3D stacking thermal management as one of the binding constraints on how far the architecture can be pushed before you need the underlying node to improve anyway. The packaging buys time and performance on specific workloads. It does not permanently substitute for node advancement. China knows this. The packaging investment and the continued push on domestic node development are not alternative strategies. They are parallel ones. SMIC's N+2 process, whatever its precise nanometer equivalent, is not the end of China's process roadmap. It is the current ceiling of what SMIC can produce without EUV. The question is how long that ceiling holds before either the equipment restriction erodes or domestic alternatives to EUV emerge at viable yield rates. On the equipment front, the restriction is holding less cleanly than it was designed to. ASML's EUV machines remain blocked, but deep ultraviolet lithography, DUV, the generation before EUV, was not restricted until October 2023, and the machines shipped before that date are operating in Chinese fabs right now. Shanghai Microelectronics Equipment, China's domestic lithography company, has not produced an EUV-class machine. What it has produced, quietly, is incremental improvement on DUV-class tools that extend the usable life of that generation. Not a replacement for EUV, an extension of the runway. That runway is longer than the original sanctions architecture assumed. Here is the reversal that the data forces. The Western semiconductor strategy was built on a model of linear dependency. China needs leading nodes. Leading nodes need EUV. Therefore, controlling EUV controls China's chip trajectory. That model assumed the performance gap between restricted and unrestricted technology would remain wide enough to matter strategically. Advanced packaging is not closing that gap uniformly. It is closing it selectively in the specific workload categories that define near-term AI competition. And near-term AI competition is not an abstraction. It is autonomous systems, signals intelligence, large-scale surveillance infrastructure, and the inference engines running China's domestic technology platforms serving 1.4 billion users. The gap that remains is real. The gap that has already closed is also real. Holding both of those simultaneously is the only accurate way to read the current situation. What this means for ordinary people outside the semiconductor industry is less obvious than the technology story, but more consequential. The AI systems being built on Chinese packaging infrastructure are not staying inside China's borders. Huawei's telecommunications equipment, running on domestically integrated silicon, is deployed across Africa, Southeast Asia, the Middle East, and parts of Europe. The inference capabilities embedded in that infrastructure don't require H100 class training performance. They require good enough inference performance at low enough cost to undercut Western alternatives on price. That is a packaging problem, and it is increasingly a solved one. There is a procurement pattern worth noting in the 2023 and 2024 import data. Chinese companies have been accelerating purchases of older generation semiconductor equipment, wire bonders, flip chip assembly tools, substrate manufacturing lines that fall below the threshold of export controls. Not because older equipment is better, because older equipment, combined with process engineering sophistication, can be pushed further than its original specifications suggested. The same institutional knowledge that JCET absorbed from Stat's chip hack a decade ago is now being applied to equipment that nobody thought needed to be restricted. This is how technology transfer works when the obvious channels close. It gets granular, it gets patient, it shows up in equipment import manifests that nobody reads. The sanctions were not wrong to target EUV. EUV is genuinely the critical path for sub-3 nanometer production, and that restriction has real bite for frontier logic at the absolute leading edge. But the policy was built around one variable in a system with many variables, and the system has been adapting to that constraint for 6 years now, with considerable engineering discipline and capital allocation that does not look like improvisation. Washington is not unaware of this. The October 2023 expansion of export controls to include more DUV equipment categories and a broader range of chip design software was a direct response to watching the packaging and DUV extension strategy develop. Whether that expansion was timely is a different question. 6 years into the most aggressive semiconductor export control regime the United States has ever constructed, the honest assessment is this. The controls worked on the problem they were designed to solve and are working less well on the problem that actually developed. China does not have EUV lithography. China does not have 3 nanometer production at scale. The leading edge node gap is real, it is measurable, and it has not closed. On those specific metrics, the policy achieved what it targeted. What the policy did not anticipate was that the target would move. The semiconductor industry's center of gravity was already shifting toward heterogeneous integration before the first export control was signed. The physics of transistor scaling were already producing diminishing returns at the leading edge, not because the engineering stopped improving, but because the costs of improvement were compounding faster than the performance gains justified. A 3 nanometer chip costs roughly 3 times as much per transistor to produce as a 7 nanometer chip did 5 years ago. The industry was going to disaggregate regardless. Chiplets were going to become standard architecture regardless. Advanced packaging was going to become a primary competition axis regardless. The export controls accelerated China's move toward that axis. They did not create it. That distinction matters for how the next phase of policy gets designed, because the next phase is coming. There are active discussions inside the Commerce Department's Bureau of Industry and Security about expanding controls to cover advanced packaging equipment and substrate materials. Specifically, the high-density fan-out wafer-level packaging tools that enable the kind of chiplet integration China's packaging houses are scaling. Whether those controls get implemented and how quickly will determine whether the current packaging window China is exploiting remains open for another 2 years or another 10. My read on this, and I'll be direct about where the evidence ends and inference begins. The controls will expand. They will arrive later than the technology development they're targeting, and the gap between policy timing and industrial reality will remain the primary vulnerability in the Western semiconductor strategy. not because the policymakers are incompetent, because the system they're trying to slow is large, distributed, capitalized, and has been adapting continuously since 2019 with a specificity that centralized policy processes structurally struggle to match at the same speed. The prediction I'll stake on the current trajectory. By 2027, at least one Chinese-designed AI inference chip built on domestically integrated packaging architecture will achieve benchmark parity with a mid-tier NVIDIA product on the workloads that matter for large-scale deployment. Not the H100, not the B200. The tier below that, the workhorse inference silicon that fills data centers. That is the competitive threshold that changes procurement decisions across the markets where Huawei and its downstream partners operate. And that threshold does not require EUV. It requires exactly what China has been building. The node war framing was always a simplification. Nodes are one dimension of chip performance. Bandwidth, latency, power efficiency, integration density, yield at volume, cost per useful operation. These are the dimensions that determine whether a chip wins in a market, and several of them are now being competed for on terrain, where China's restrictions are less binding than the original strategy assumed. There is something almost methodical about how this unfolded. Not chaotic, not desperate. A constrained system identified the degrees of freedom available to it and allocated capital and engineering talent into those degrees of freedom with patience and consistency. Whether that reflects central planning working unusually well or simply the logic of any large industrial base responding rationally to constraint is a question I find genuinely unresolved. What is not unresolved? The assumption that controlling the leading edge of lithography would control the leading edge of AI-relevant compute has not held cleanly. The leading edge moved, and the equipment needed to compete on the new leading edge was not, for most of the critical window, on any restricted list. If this analysis is useful, share it with someone who still thinks the chip war is only being fought at the nanometer level. The more interesting fight is happening in the packaging layer, and it has been for years.